Okay, exercise 4. Calculating the pH of a 0.75 molar aqueous solution of sodium cyanide. What you should notice here, sodium cyanide is our compound. They're not basically saying instantly that this is an acid or a base. It's just telling you a salt. However, you can probably tell that it has something to do with acids and bases because they gave us AKA for hydrocyanic right here, like so. So, we look at the salt though, and we have to evaluate the salt so we know what type of reaction we're going to be dealing with. And since it's an aqueous solution, we know it's going to be in water, so water will be the other reactant. Sodium cyanide though, thinking about what we just talked about in terms of the salts, is this one going to be an acidic salt, a basic salt, or a neutral salt? So what do we know? We have the cation, that's sodium here. We have the anion, that is cyanide. Is sodium cation, is that neutral or is that acidic or basic? What type of cation is that? Neutral, acidic, or basic? What we got going on there? Sodium is going to be the cation of sodium hydroxide, which happens to be a strong base. So what type of cation is sodium going to be? What is always the cation and anion of the strongs? Usually the cation or the anion of the strong acid or strong base, those ones are going to be neutral. So the sodium is going to be neutral. So it's going to stay neutral and it's not going to react at all. How about the cyanide though, and hydrocyanic acid? Cyanide is the conjugate base of hydrocyanic acid. Is that one going to be basic? You should know your 7 strong and know that hydrocyanic is not a strong acid because it's not one of the 7 strong. The other indicator to you up here though as to hydrocyanic not being a strong acid is that they give you the Ka value, which is really low number. So that means cyanide is the conjugate base of a weak acid. And we know conjugate bases of the weak acids, these guys are going to be basic or alkaline. So what is actually occurring here is the cyanide, when we break apart the sodium and the cyanide, because it is a soluble salt, anything with alkali metals is soluble, so, and sodium's an alkali metal, the cyanide isn't just going to sit there and float around and be surrounded by water. It's actually going to react with water. And it's going to pull off an H. So we know the cyanide part is going to react with water. The sodium, though, is just going to happily float around with the oxygens facing in of the water, and it's just going to get surrounded and sit there and float and not react. So really our reaction that we're dealing with here for that particular salt is going to be the cyanide reacting with the water. And that, of course, is going to pull off an H. When it pulls off the H, you get hydrocyanic acid and hydroxide. And that's why it's basic, because it's going to produce some hydroxide in our solution. Now, because this is a basic solution, we know it's going to cause a reaction here. We're going to need to know something about our base. They did not give us the equilibrium constant for our base here, or the ionization base constant. Instead, they gave us the Ka. So, what can we do to find our Kb here? What can we do? How do you find Kb from a Ka? What is that equation we can use? Anyone? Yes, that's exactly right. We can do the KW equals the KA times the KB. So KW, KA times the KB. We know, since it's not telling us different, we know that we're at 25 degrees Celsius, so 1 times 10 to the minus 14. Here is our KA, 6 times 10 to the minus 10, times the KB. And what is our KB then? Because we need to know that for our calculation here. What do we get for our KB? What is KB? Calculate it. What do we get? What do we get? Yeah, that's exactly right. 1.6 times 10 to the minus 5. KB, stronger number here. Definitely beats out the self-ionization of water in terms of its strength here. Now we can just do the calculation because we know KB. And we know our starting amount, 0.75 molar. We can kind of skip the rest of the rice table, right? Because the water doesn't count. This is going to be X, this is going to be X, and this is going to be 0.75 minus X. Then all we have to do is write out our expression. So KB is going to equal hydrocyanic concentration times hydroxide concentration, products over reactant, the cyanide, like so. And we just plug in our variables and calculate. So we get 1.6 times 10 to the minus 5 is equal to x squared, because x times x, over 0.75 minus x. Now what can we do to that x on the bottom? What can we do there? Since we have a 0.6 times 10 to the minus 5. 5% rule, definitely. Eliminate x. Eliminate x, the 5% rule. Very good. No, it's going to be too small. Then we go ahead and calculate x. Now remember, x is going to give us our hydroxide, which is what we need in order to calculate the pH. It gives us the conjugate as well, or the acid, but we really need the OH to figure out the pH. So what is our x value here? What do we get for hydroxide? Which equals our x. What is the concentration of our hydroxide that got produced here? Yes, very good. Yes, times 10 to the minus 3. That should be correct. 3.5 times 10 to the minus 3, or it might look like this in your calculator. Molar. Then it just becomes using your negative log of the hydroxide gives you the POH. Remember, we got the negative log of the hydroxide gives you the POH, and then the 14 equals the pH plus the POH. Using those equations. So what is the negative log of our 0.0035? What do we get for that? That's going to give us our POH. So what do we get here? Looks like getting 2.46. All right, I'm going to go with 2 significant figures since there's 2 in our concentration, or 2 decimals, excuse me. And then we subtract that from 14. So 14 minus 2.46. 14 minus the 2.46, this is going to give us 11.54 for the pH. So that sodium cyanide salt actually drove the pH up quite a bit, up to 11.54. So that's pretty significant. Pretty strong conjugate base there, but the hydrocyanic is a very weak acid with a 10 to the minus 10. So just going to walk you through the steps here. Once again, the cyanide is going to dominate over self-ionization of water. Basically, that happens pretty much all the time except for the one scenario you saw in the first set of notes where there was such a tiny small amount of acid added that it was not going to take over. And that's only really been on the AP exam like once or twice. We definitely went and found Kb using our Kw equation. Then we set up our rice table, or modified rice table. But you could set up the whole thing if you want to. Write out the expression, plug in the numbers, calculate for x, eliminate x using the 5% rule. Negative log of the hydroxide gives you the POH, and then 14 minus POH gives you pH. All right, let's talk some Lewis acids, Lewis bases. Kind of briefly went over those in that equilibrium lab because we were using complex ions in there. But the Lewis acid is the electron pair acceptor, the Lewis base is the electron pair donor. So it's kind of opposite. We think of the Bronsted-Lowry acid as the proton donor, but here the Lewis base is actually the donor, the electron pair donor, instead of the proton donor. So they're kind of opposite. What you need to focus on here in terms of the metal, especially here the hydrogen, is going to be able to accept a pair, and the ammonia is going to be able to donate a pair. Now, if you really think about the structure of ammonia, if you were to draw it, looks like this. Okay, remember it's a pyramidal shape molecule. This pair at the top here is going to be the pair that gets donated. And then the hydrogen can attach to it, and then it forms a nice tetrahedral polyatomic ion. So this would be describing how ammonia forms ammonium when it adds an H on in terms of like the Lewis acid structure. Lewis acid, Lewis base 2 for forming these complex ions. Lewis acid is going to be the aluminum. Lewis base would be the water that gets added in, and water has 2 electron pairs it can donate. So this one forms a complex ion, the aluminum plus the water. Not going to go into too much detail, but a lot of your Lewis acids and bases form the complex ions this way. Remember the cobalt complex from the Le Chatelier principal lab and stuff? Those were complex ions there. A lot of them followed this Lewis acid, Lewis base model. And the metals, these metal ions are going to be your cations usually. And then they add on like ammonia, cyanide, thiocyanate, hydroxide, various different ones. Or no, this was thiosulfate. This is thiocyanate. As you can see, and they typically form in these ratios as being having to do with the charge on the metal. The charge on the metal is +3. It can end up accepting up to 6 pairs. Typically, not that we're going to go into that much detail, but complex ions fall under this Lewis acid base category. Also, complex ion, the metal ions at the center with the other molecules or ions surrounding it, and it's how it's actually bonded with the pair being accepted and donated. It forms something called a coordinate covalent bond or a dative bond. That would be the terminology for it. Not that it's that important, because it's not here in this copper is the metal ion in the middle, +2. As you can see, +2, it's adding in 4 pairs of the ammonia, and it ends up forming the complex ion. Once again, these are ones that they could use in free response questions. Just follow the regular chemistry with it, though. Shouldn't be anything out of bounds. And, you know, they use them a lot because they form pretty colored solutions and things, and it's easily done in Beer's law and other things. All right, here's a chart that compiles all 3 models or definitions for the acids and bases. Renius produces hydrogen in solution, hydroxide in solution for the acid-base definition of Bronsted, Lowry proton donor, proton acceptor, Lewis acid electron pair acceptor, definition of the base, electron pair donor. One other thing I wanted to go back over real quick is the solubility effect when you decrease the pH, where you make it an acidic solution, you're dumping the salts in. Solubility of compounds containing basic anions, so now you know what a basic anion is. It's the conjugate base of the weak acid that make the pH go up. Remember, these guys increase the solubility of these insoluble salts. Looking at this diagram, this is lead to fluoride. So if you increase it and you have H plus floating around, what's going to happen is the fluoride is going to actually bind with the H plus and form hydrofluoric for the most part. There is a little bit of an equilibrium there, but for the most part, it's going to remove the fluoride from the solution. And if you remove fluoride from solution, that's going to make more fluoride as well as the lead dissolve, right? This is the KSP, where the 2 fluorides plus the lead. So it's going to push it to the right where you're dissolving more ions, so it makes it more soluble. This example over here should make a little bit more sense to you now, because this is I floating around in there with the PBs, and this is lead to iodide. Now if you remember, I, that anion, is actually the conjugate of HI, which is hydroiodic acid. Iodic acid. This one happens to be a strong acid. So this one happens to be a neutral anion. So it's not going to react with water. That's why in this particular case there's no reaction. It's not going to increase the solubility because the I is not reacting with water. It's not reacting with H pluses. It's not going to allow for more salt to dissolve. So basic anions, remember, in lower pHs are going to dissolve more of the salts. This is from Unit 7, the same slide from that one, just to remember it's a Le Chatelier idea, because basically when you add it to a, you're adding it to the lower pH solution where there's hydrogen floating around, you're essentially removing fluoride, which pushes this one to the right and shifts to the right, creating more dissolved ions. So I just wanted to review that real quick. Also, for the insoluble hydroxides, remember adding H plus there also. This is a neutralization effect, because remember you add H plus to hydroxide, that's going to create water. So it's essentially moving hydroxide, which pushes this one to the right, shifts it to the right, and more of the salt will dissolve again. So factors affecting solubility, if it's a insoluble hydroxide, or if it's a basic anion idea, if you're in a lower pH solution, it should dissolve more of the insoluble salt with the KSPs. And this slide is also back in Unit 7, but you can review it here, because this does pertain to our acid-base discussion, and it links in the solubility part as well. So as you can see, if you have an acid-base problem, they could throw in some KSP stuff at the end with the Le Chatelier for you to look at.